The first problem I will be covering is permutation addition. So in this problem, you are given a sequence of n numbers and you can do multiple operations on that array. In one operation, you can take a permutation a1 to an and replace p1 to pn with pi plus ai for I from 1 to n. So I'll just write it down. So you can take any permutation p1 to pn and you have a array a1 to an. In one operation, you can replace a1 to an with a1 plus p1, a2 plus p2, a3 plus p3, and so on till an plus pn. The goal is to make all the numbers in the sequence equal, and we can do at most 10,000 operations. The constraints are n is at most 50 and all the elements of the array are also at most 50. So did everyone understand the problem statement? Okay, I will send the link. So one observation you can make is that after all the numbers are equal, the sum. So suppose after at the end a1 equal to an equal to an equal to x, then the sum is x into n, which is divisible by n. And now notice that in any operations, the sum is replaced by sum plus n into n plus 1 by 2. So it must be possible to add n into n plus 1 by 2 sometimes such that the sum is divisible by n. So now notice that n by 2 divides n into n plus 1 by 2. So either summation ai, n divides summation ai, or n divides summation ai plus n into n plus 1 by 2. In the latter case, we can just do any random operation to get the first case. So we can just do any random operation and get the first case. So this will take only one operation. Did everyone get this? Okay. So notice that we add a permutation. So the numbers are 1 to n. The sum of those numbers is n into n plus 1 by 2. So sum gets replaced with sum plus n into n plus 1 by 2. Now, so after some operations, the sum must be divisible by n at the end. So now notice that n by 2 divides this number. So either sum is n divides the sum or n divides the sum plus n into n plus 1 by 2. So did you all get this part? Okay. So now after doing at most one operation, we have an array a1 to an and n divides summation ai. So now let x be the average of summation ai by n. Now notice that if all the elements are equal, then we don't need to do any operation. If all elements are not equal, there must exist an element y is less than x and also an element z, basically ai is less than x and is x is less than aj. For some I comma j, this must hold. Since the average is x, if one value is less, then there must be one value more than average also. So did you all get this part? Okay. So now a hint is that we can do some operations which can make both ai and aj closer to the average than before. And doing these operations repeatedly can help us make all the numbers equal. Notice that only the relative differences between the numbers matter. The number actually does not matter even if it grows very large. Which there's a limit of 10,000 operations, so that must be kept in mind. So now I will show a construction. So in the first, we take a permutation which has numbers 1 to n, and the second one we take the reverse permutation except the first two digits are swapped. So it's n minus 1, then n, and then n minus 2, and so on. So now if you notice that n plus 1 gets added to all numbers indices greater than 3, n plus 2 gets added to index 2, and n gets added here. So now notice that the second number increases by 1 relative to the others, and the first number decreases by 1. So now instead of taking the first and second indices, we can do this for the ith and jth indices taken over here, and we can then add n to this, n plus 2 to this, and n plus 1 to remaining. If you notice that x changes to x plus n plus 1, this will change to aj plus n. So now it's closer to the average by 1, and this is also closer to the average by 1 since it gets increased by 1 relative to the average. So did you all get this part? Okay. So now we are almost done. Now we need to count the number of times this can happen when ai is less than x and is less than aj. So we do at most one operation in the beginning. Now notice that ai is less than equal to 50 in the constraints in the beginning, and after at most one operations ai is less than equal to 100. So now notice that the sum of the numbers is at most 5000. So now if x is the average, the summation of x minus ai, this is the average, this is the number of times something needs to be decreased or increased. This is less than 100 and there are 50 numbers, so this is less than 5000. X is also less than 100 by the way. So this is also less than 5000. Did you all get this part? That the sum of differences between the numbers and the averages is at most 5000. Okay, so I will like try to explain it once more. So now if x is the average, then the number needs to be changed by ai minus x relative to the other numbers. So now ai is less than 100 and x is also less than 100. So this number is less than 100, and there are at most 100 n operations. This is 5000 around prox. And now in each or type of operation we try to increase one and decrease one at the same time. So we in two operations we change this decrease this value by 2. So we only take 5000 operations and we have a limit of 10,000 operations, so we are basically done. I will show my code to this problem. So here if n is odd, then n into n plus 1 by 2 is divisible by n, and the sum is, if the sum is now not divisible by n, the answer is no. In the other case we check by doing one random operation. Here we add the permutation to it and check if it's possible. So now we try to find the average. We try to find one number less than the average and one number more than the average, and then we do the operation which I mentioned over here, to add n plus 2 to one, n to the other one, and n plus 1 to all the other numbers. Basically similar. So we basically take a while loop to find the average, and if all numbers are not equal to the average, we just keep iterating the process. And I showed that it we take at most 5,000 other nodes, and at the end we print the answer. So did everyone understand the solution to this problem? Like if you have any doubts, you can unmute and ask. Okay, so now I will do a slightly easier question. So we are given a n into m grid, and each cell is painted either white or blue. Now we are given q queries, and in each query we are given a subrectangle. So basically, we have a rectangle, and in each query we are given a subrectangle, and we are asked to find the number of connected components inside the subrectangle if we consider only blue squares. So suppose these are blue, then there are two components here. The rest are white. And now another information given in the problem is that for any two blue squares, there is at most one simple path between them. A simple path is a path which does not visit any square more than once. So basically, the graph is a set of trees or a forest, and we are asked to solve q queries. Now q is very large, so we need to solve every query very fast. So I will give you like 1 2 minutes to think about it. I will just draw a random grid, which is possible structure. So this subgrid has two components. If we see another subgrid, say this, notice that in a simple path, when we are counting the components inside a subgrid, we can't visit squares outside of it. So here, this is one component, and this is another component. So there are two components over here as well. And if you notice the constraints, n and m are around 2000, and q is at most 2 lakh. So this is a possible sample. They have given a nice image also. So in this query there are two components. So now a hint I will give is that in a tree, number of edges plus 1 equal to number of nodes. So basically the difference between number of nodes and number of edges is exactly 1. Now if you notice in a forest, number of nodes minus number of edges is equal to number of connected components. So this is true because every tree contributes 1 to the number of nodes minus number of edges difference. So now if we sum it over all trees, it gives us the number of trees, which is the number of components. So now for a subgrid, we need to be able to query the number of nodes inside it and the number of edges inside it. So the number of nodes inside it is basically the number of blue cells. We can count the number of blue cells by 2D prefix sums. We can also, and an edge is a, so for edges, we basically take two consecutive blue cells, and if there are in a row, then the horizontal edge is there. If there are two consecutive blue cells in the column, then a vertical edge is there. We need to be able to query the number of edges in a subgrid also. So for a horizontal edge, we assign the leftmost node as the value, and instead of querying the number of edges in the whole grid, uh, in the separate prefix sums, we query by deleting the last column, we query the number of edges here. So for each horizontal edge, we add 1 to the leftmost node, and for a vertical edge, we add 1 to the topmost node. And now for a subgrid, we remove the last row and count the number of prefix sums, number of edges which the top node marked here. So basically, we maintain three prefix sums: one for the blue cells, type 1, one is for the horizontals, and one is for the vertical. So we need to make sure that we don't count edges with one cell inside and one cell outside. That shouldn't be done. And so this way we can find the answer. I will also show how to calculate 2D prefix sums. So suppose we are given a grid and we need to query the sum of numbers in a subgrid. Then this can be done in order 1 offline after some pre-computation. So basically we try to, for each cell I comma j, we maintain sum ax comma y with x is less than I and y is less than j. The transitions are as follows: ax comma y equal to ax minus I plus ax y minus 1. Not ax, sorry, this will be b minus bx minus 1 comma y minus 1 plus ax comma y. I will show why this holds true. So suppose this is the grid from the top left to the square with coordinates I comma j, and to maintain the sum, we know the prefix sums of the other subgrids which have some value less than x or some value less than y. So now if we add this area gets added for bx minus for bx y minus 1, this area gets added. Now if we add bx minus 1 and y, then this area also gets added. So now notice that this area gets visited twice and we need to subtract it. This is exactly bx minus 1 comma y minus 1. So we can just subtract it. And now we need to add the value of our current square, which is ax comma y. With this, we can find the number of sum of cells from the top left to some cell. Now, if we want to query the sum of a subgrid, then now this can be done in order 1. So suppose we need to query the sum of this subgrid. We know the sum of this subgrid. Basically, I will mark it with a separate color. We know the color of this subgrid, so we can add it. I'll just mark it once with one color. This gets added as, say, this is L2 comma R2, this is L1 comma R1, So we can add B L2 comma R2. Now what we do is we subtract this area outside the subgrid. So we subtract B L1 minus 1 comma R1. Now we subtract this area minus B. This is actually R2. B R1 minus 1 comma L2. So now if you notice, these areas are cancelled out. These areas are cancelled out. This is cancelled out. This is counted once and this is counted twice. This is subtracted twice, and like we added it once, so we need to add it again. So now we add B L1 minus 1 comma R1 minus 1. So now the contribution of this area is 0, this is 0, this is 0, this is 1, this gets counted once, the sum here, and this is 0. So we get the sum in a subgrid. So did you all understand how to calculate the sum of numbers in a subgrid? Okay. So now this problem is basically solved, since we can just calculate the number of nodes minus number of edges in that subgrid. So now I will move on to the next problem, which is median sum. I sent the link in the chat. So basically what this problem states is that you are given n numbers. There are 2 to the power n minus 1 non-empty subsequences of that array. We list the sums of all the subsequence in non-decreasing order, and we have to find the median of median of this list. Note that we do not take the empty set. So we only take non-empty sets. All integers, all numbers are positive. So if you look at the sample 3 comma with n equal to 3 and 1 to 1, this sum of all the subsets is 1 comma 1 2 2 3 3 4. Basically I will list it out, all the subsets. The array is 1 comma 2 comma 1. So if we take one number, we get 1 2 1. If we take two numbers, we get 3 3 2. And if we take all, we get 4. So we get 1 1 2 3 3. We get two twos and 4. We have 7 numbers and we print the median of this list as 2. Now the interesting thing is that n is 2000, so we can't simulate over all the sums, and we need to find the minimum sum fast. All the numbers are also at most 2000. I will give a hint that you try to include the empty set 0 also inside of this. So you include 0 also, and at the last you have the sum of entire array, summation ai, and you have some numbers in between, and you need to find the median. So here we have 2 to the power n numbers, and we need to find 2 to the power n minus 1 plus 1th number here after including 0. I will give you a few minutes, 1 2 minutes to think. Okay, so now I will give a hint. The hint is that the first and last sum add up to summation ai. Now, if you take a set S and its complement T, so basically T equal to complete set by S, then sum S plus sum T equal to summation ai. So now, if you notice that each set has only one complement and the complement of that set, so like complement of S, if we take complement twice of S, we get S only. So basically, we form 2 to the power n minus 1 pairs of sets of complements. Now, if you notice that if a suppose we have 2 to the power n minus 1 pairs and we list the sums of them. So let a1 be okay. So suppose with that we choose s such s and t such that the order that sum s is less than equal to sum t. So now if we list down the pairs A1 B1, let's take it B1 C1, B1 C1, B2 C2, and B to the 2 to the power n minus 1, C2 to the power n minus 1, and such that Bi is less than Ci. These are the pairs of complements. Then you notice that Bi is less than equal to summation Ai by 2 for all I, and Ci is greater than equal to summation Ai by 2 for all I. Now, suppose that we sort all the Bi and Ci by Bi, then Bi is less than equal to B2 is less than equal to B2 to the power n minus 1. And now notice that the sum of the complements will reverse order as sum s equal to constant minus sum complement s. So now C2 to the power n minus 1 is less than equal to C2 to the power n minus 2 and so on. C2 is less than equal to C1. So now if you notice that the sums are listed in increasing order and all the Bi sums form the first half of the subsets and all the Ci sums form the second half of the subset. We needed to find the 2 to the power n minus 1 plus 1 subset. Now notice, as I showed earlier, this is less than equal to ai by 2 and this is greater than equal to ai by 2. And now notice that if bi equal to summation ai by 2, then ci is also equal to summation ai by 2. So those forms kind of consecutive pairs. And so now if we see the first sum, which has like the smallest sum, which has sum at least summation of all the numbers by 2, then that will be the answer. So we try to find smallest subset sum is greater than equal to summation ai by 2. Note that if it's exactly half, then there is one exactly half in the other one also, so it doesn't affect the ordering at all. So did you all get that we need to find the smallest subset sum greater than equal to summation of all numbers by 2? No, bi and ci are not summation ai by 2. Basically what I meant was, if one of them is half, then the other one is also half since we subtract it from the total sum. So both will be same. So what I want to say is that it's not possible that if so basically what I want to say is that if there is a bi with sum equal to summation ai by 2, then this also has sum equal to ai by 2. So in that case, if this sum is possible, this is the answer, since this will be the 2 to the power n minus 1 subset. So did you all get why we need to find the smallest subset sum, which is at least half of the total sum? Since we can take complements and one will be at most half of the sum and one is at least half of the sum. Okay. So now what we need to do is, now notice that n and ai are small. So summation ai is less than equal to 2000 square. We can maintain a dpij if sum j is possible by taking subset of first I elements. So it will be 1 in this case and 0 otherwise. Now our dp I plus 1 comma j equal to max dp I comma j. Basically we check if it's already possible in the smaller prefix, or if we can add the current number and make it possible. So if either of these is 1, we can this is also 1. So basically this is standard knapsack dp, and now this will be n into ai max ai square. This is still too slow, since this is 2000 cube and this won't fit. We need to make it to quadratic time or something similar. So now a trick we use here is bit sets. So basically bit set, we can maintain sort of an array of zeros and ones, and we need to declare the size beforehand. Like we can't make it according to a random variable, but it should be a fixed constant. So here will be make a bit set of say 2000 into 2000 plus 1, say, like we can make this of this size bit set. And so the interesting thing about bit sets is, if there are two bit sets a and b, you can find and ab or ab xor ab a shifted by j bits to either end. We can shift it. So suppose this is size, we can do these operations in size by constant. So on 64-bit computers, the constant is 0. So basically, you can do operations in size by 64 operations. Instead of, if you do normally with brute force, this will be size. So bit sets really speed things up. They are made in such a way such that they store only zeros and ones. So now notice that to calculate the max of these, we basically take OR of DPI and DPI shifted by AI plus 1. So we shifted the indices down by AI plus 1. So AI plus 1 goes to 0, AI plus 2 goes to 1, and so on. The indices smaller than AI plus 1 get deleted. And so this is the max operation. Since the numbers are 0 and 1, we can just take the OR of them. So now we have solved the problem in 2000 cube by 64, and this will easily pass. I will show my code. It is very short. We just, and now at the end we just find the smallest subset sum which is more than which has sum at least half of the array. So here we maintain, this is my DP. Here we have firstly only the zero sum is possible, and now we or it with this the current DP shift and the DP shifted by the current number. And now we check the smallest number which is at least half of the sum and print it. So did you all get the bitsets part of the code? Okay, shifting part is basically, this is a bitwise shift. So I will give an example with numbers. So suppose this is the bit set. Now if you shift it to the left by 4, the first four number disappear. We just get 1 comma 1 comma 0 comma 0, and the non-existing numbers get replaced by 0. So basically, if you think this is number in binary form, it gets divided by a big power of 2. We can also shift it to the other side. Did you get this part? Okay, so now this problem is also solved. Now I will move on to the last problem for today, LEQ and NEQ. So basically, you are given a sequence of integers a1 to an. You have to find the number of sequence of n integers such that the ith number is between 1 and ai, and no two consecutive elements are same. So now if the second condition was not here, we could just print the product of all the ais, and that would be the number of sequences. So for example, if these are the numbers, these are the possible sequences. Note that we can't take 111, 112, or 211, since two consecutive elements are similar. N is around 500,000, so you need a fast solution, say linear time or n log n. So I will try to model the problem in a slightly different way. So let xi be the set of sequences with ai is not equal to ai plus 1. So we have n minus 1 sets. We need to find x1 intersection x2 intersection x3 intersection xn minus 1. Now notice that we can use inclusion exclusion in this. So this is basically x1. So now like we can take x1 plus x2 and so on till xn. We will try to find all the sequences which violate this. So basically, if either condition of this is not satisfied, so the general inclusion exclusion statement I will just write it. Not the general, I will like show it for a small case. So now notice that if there are four sets, then you write in this form. And so on for even size subsets you subtract them, and for odd size you add them. For even size you subtract, and for odd you add. Now we need to find when all of these conditions are satisfied. So if like if we can find to find this the intersection, we can find all the other ones intersection, like try to formulate it in such a way that we can find, and then we can like somehow subtract it from the total number of sequences. So now for the sequence A2 to AN, for a prefix AI, we try to find the number of subsequences in which we have shift like fixed x indices, where the consecutive elements are certainly different. Like the remaining can be different or can be same also, but for these x pairs, we need to find the number of ways to select a subsequent sequence of the first I elements, and also to select x pairs such that they are different. So in this way, we can find the intersection of, say, the x elements, x sets, when the x conditions are certainly satisfied. And so we also need to maintain if the x is odd or even. So instead of maintaining x, we only maintain parity of x. So did you all get this part, how we formulate the condition with sets, where xi denotes a set of sequences with ai and ai plus 1 different. So xa b1 intersection x b2 intersection x b3 and so on till x bk denotes that a bi is not equal to a bi plus 1. The remaining pairs, the n minus 1 minus k pairs which are not covered, they can be anything, but we need to make sure that these are different. So we try to find a number of ways to count this. So now instead of counting when they are different, we can count the number of pairs which are same and like sort of subtract it. So instead of counting number of different, this is like we formulated in slightly different way. So if we can find out that this pair k pairs are same, so say suppose we like I will try to give a smaller example with say four numbers. I will like give you a few minutes to think about it first. Like how will you shift the formulation from the different one to the same one, and then you can like handle it in a very similar fashion. Okay. So for the x part, xi is the set of sequences where ai not equal to ai plus 1. So now instead of this, we this was just to like give a hint. We formulate the number of with yi equal to set of sequences with ai equal to ai plus 1. I will also clear the initial frame since it has a limit of 20. We'll try to explain. Let yi be set of sequences. So we need to find total number of sequences minus yi union y2 union yn minus 1. So if either of these conditions is satisfied, we don't count that sequence and we subtract it from the total number of sequence. So did you all get this set part? Did you all get the like how yi is defined and how yi union y2 and union till yn minus 1 will give the number of sequences which violate any one condition, at least one condition, and we can subtract it from the total number of sequences. This is basically product of all ai, and we can just subtract it. So now notice that using inclusion exclusion we can write it this as summation of. So for example, I will just give, if there are three numbers, we can just write a plus b plus c minus a intersection b minus a intersection c minus b intersection c plus a intersection b intersection c. So if you notice that now set sizes are added up. So since this is a subtraction size, odd set sizes are subtracted and even set sizes are added. So let dpi 0 comma 1 denote parity of the. So now notice that if we know the number of parity of where ai equal to ai plus 1, if we know the number of pairs we are considering, then we also know the number of pairs which we are not considering, which is this. So instead of maintaining k, we maintain the parity of n minus 1 by k, and then we can add and find the parity of k and add the answer accordingly. So we maintain. So we basically what we do is we try to break the range a1 to an, 1 to n in separate subranges, and we count the parity of the number of gaps between them. Note that if we want a subrange all to have equal elements, then there are min, al, al plus 1, and so on till ar ways to select the number. Since like this main condition should be satisfied if we are taking the range l to r, we have this many ways to select the number. We take this product over all ranges, and we try to find the number of the sum of all the products if we break it into an odd number of ranges or an even number of ranges. So now notice that dpix equal to summation dpj 1 minus x. Since we are shifting a sequence, this will get flipped, the bit will get flipped into min aj plus 1, aj plus 2, and so on till ai. Did you all get this part? Okay. So now if you calculate this naively, this will be n square. We cannot do this naively over all j. This is simply not possible. So now notice for the index ai, we find the largest aj, largest j such that aj is less than ai. Aj is, and so if there are numbers till ai, the min for all subranges which end after j is ai only. Since all these numbers are like less than say ai, more than ai, so this is basically the next smaller element to the right. And so now we maintain prefix sums over the dp, so we can like query sum of dpj x for j in l to r. For a fixed x, we can maintain prefix sums and we can query it. So now we break this part summation into two parts. One is for ranges ending after the next smaller element. So for them, this is basically summation of dp k 1 minus x into ai for k from j to I minus 1. I minus 1. We basically take k from I to minus j to I minus 1, and we can get the sum of this. So now an interesting fact to notice is that in this case, if we are ending the range before j or at j, then all the elements from j to ai, so xj equal to xj plus 1 equal to xi. So now notice that all these elements are same. So now if you look at the summation value, this is exactly dpjx. Since the number of elements are not, the number of ranges is not changed, the parities remain same, and the min element also does not change. So basically adding these greater elements does not change anything. So we can add dpgx to this summation over here. Did you all get this part of the dp? Okay, so I can show the code over here. We find the number of total number of sequences by the product of all elements. Here we are finding the next smaller element to the element. We find the next smaller to the left. dpij denotes the dpi showed. Pre-ij denotes the prefix sums of the dp. Now notice that basically what we are doing is we are trying to find this summation dpk for k in some range for a fixed x. So to dpi plus 1 0, we add the prefix sum with dp for 1 and multiply it by the current element. Similarly, we do it for the flipped bit x. And at the end, we also add the dp values for the left element. Since this summation remains unchanged for elements less than equal to j, basically I will write it formally once again. dpk x 1 minus x summation into min ak plus 1 ak plus 2 till ai. Now if we take only k is less than equal to j minus 1, then notice that this equals to dp k 1 minus x into min ak plus 1 ak plus 2 and so until ai aj. Now notice that aj is in between and aj is less than aj plus 1 till ai. So the min element remains unchanged, and this is basically nothing but dpjx. If you notice the recurrence here, this is exactly same. We are iterating over j is less than I. Here we are iterating k over k is less than j. It's exactly same, and so we can just add dpgx to dpix. So did you all get this part now? Okay, so I will just show the code. So here we are adding the dp of the left smaller, like next smaller to the left, and for the values in between next smaller and I, we add the dp with the bit x flipped. We basically just add it. The main element is ai, so we can just multiply it. So I hope you all understood the problem solution. Now this was like harder than the other three problems. So I will end the session for now. Thank you.